G.N. Lewis, the person who gave us the Lewis dot notation that we learned about earlier, also showed us how we can arrange the valence electrons in a molecule or another covalently bonded species called an polyatomic ion that we're going to learn about later on. In Lewis structures, lines represent shared pairs of electrons, and by that we mean bonds, pairs of electrons that are shared by two atoms. So if I have a hydrogen and I have a chlorine, a stick, a line between the two of them represents a pair of electrons that's a bond. Pairs of dots represent unshared pairs of electrons. So on that same molecule, if I have a hydrogen to bond to a chlorine, I might see 3 pairs of dots. Those are unshared electrons, electrons that belong only to that atom. Notice how the electrons are always in pairs, either a pair that's a shared pair or a pair that's a lone pair. These unshared pairs we also call lone pairs. They're never singles. Once they're stable, once they're part of a molecule, they're not single dots. They'll always be pairs. So here's an example. A chlorine molecule. Well, we have a chlorine, we have another chlorine. These chlorines are 7s, group 7s, so that means they each have 7 dots. So this is what the individual atoms would look like. They're going to share that pair of electrons, and so as a Lewis structure, we would draw it this way. The shared pair becomes a stick, a line, and then the lone pairs, the unshared pairs, still show up as pairs of dots. Hydrogen chloride, we already did this. H bonds to Cl, and then the unshared pairs on the chlorine that make its full octet show up there. Again, you still can think about each symbol as having 4 sides, and you want to make sure that there's a pair of electrons in each side. Whether or not that pair is actually a pair of dots or not depends on if there's a bond or not. A stick counts for 2. Here's another one, oxygen. In the oxygen molecule, we're going to find out that there are 2 pairs of electrons shared between the 2 atoms. Those 2 shared electrons show up as 2 sticks, and the lone pairs again are still pairs of dots. So how do you draw Lewis structures? Well, here's the step-by-step instructions. The first thing you want to do is give the dot symbols of all the atoms that are going to be bonded. This is really only just to find out how many valence electrons you have, so eventually you're going to stop doing this step. But let's say you were going to bond hydrogen and nitrogen. You'd want to draw that dot structure, and you'd want to draw that dot notation so you could count up the valence electrons. And in this case, we'd have 1, 2, 3, 4, 5 from the nitrogen and 1 more, and so that'd be 6 electrons. So that's the first 2 steps. The next thing you want to do is make a skeleton structure. There are several hints to making a good skeleton structure, but this involves some experience, some creativity, and sometimes some trial and error. Here's one skeleton hint. In a molecule, the farther away an atom is from the edge of the table, the farther away it's probably going to be from the edge of the molecule. So let's say you were going to bond carbon to oxygen. In this molecule, carbon is probably going to be closer to the middle of the molecule, and oxygen is probably going to be closer to the outside of the molecule because carbon's closer to the middle of the table than oxygen is. And the same thing goes this way. If you were going to bond sulfur to oxygen as part of a molecular structure, sulfur is probably going to be in the middle, whereas oxygen is going to be farther outside because going up and down here, oxygen's closer to the edge, sulfur's closer to the middle. So that's one guideline. Another guideline is this. Hydrogen, because of the fact that it only has a shared pair of electrons, and that's all, no full octet, hydrogen has to be on the outside of a molecule. So hydrogen can be attached to something like an O or a Cl or an N or something like that, but you're never going to have hydrogen bonded to 2 things. That doesn't happen. Hydrogen can only support 1 pair of electrons, that's all. So hydrogens are always on the outside. Here's another guideline. If you look at carbon, its dot notation gives a kind of a clue as to how it's going to bond. It has 4 places where it can share. Look at the 4 sides of carbon. 4 places where sharing needs to happen to make it stable. So because of that, carbon and things in carbon's column are going to tend to make 4 bonds. Nitrogen, column 5, 5 dots. Well, if you look at the 4 sides again, 3 of the sides need sharing to happen for stability. So nitrogen and things in nitrogen's column are going to tend to make 3 bonds and end up with a lone pair. Oxygen has 6 dots. And looking again at the sides, 2 of the sides need sharing to occur for stability. So oxygen is going to tend to make 2 bonds, and so will everything else in that column, and it'll tend to have 2 lone pairs of electrons. Fluorine and the other halogens are 7s, so there's only one side where sharing needs to occur. So things like fluorine are typically going to make 1 bond. They'll be on the outside, that means, of the molecule, and then they'll tend to have 3 lone pairs. So those are some skeleton hints that can help you out. Another general rule is if you're trying to decide between a couple of Lewis structures, and one is long and stringy and the other one is symmetrical and compact, the symmetrical compact arrangement is usually the best one to get started with, at least. Once you've got a skeleton, the next thing you want to do is fill up the octets of all the elements by adding valence electrons in pairs. So let's say I had this arrangement. Let's say I had a skeleton where I had my 2 hydrogens bonded to the outside of an oxygen, because oxygen is closer to the middle, and because oxygen prefers to make 2 bonds, and because hydrogen is on the outside. Those are all good reasons for this skeleton structure to exist. Now, if I look at this oxygen, it's not stable unless there is a pair of electrons on all 4 sides. There's a pair here and there's a pair here, but these 2 remaining sides are not covered by electrons, and so that means it's unstable. I fill that octet by putting in 2 pairs. Don't worry about the fact that oxygen only has 6 electrons to start with. It's not interested in being a 6-electron atom. It wants to be stable, because remember, 8-electron atoms are stable, and so it's gotten into this molecule so it could have a full 8 dots. We fill those dots in to indicate that stability. The next thing you have to do is count, and you remember you added up all those electrons in the first step. You want to make sure that the structure you've made has the right number of electrons. If it has too few electrons, well, we're going to deal with that later on. But one common problem is the structure has too many electrons. If that's the case, you want to form multiple bonds. Like this is an example. Let's imagine I'm making the structure for oxygen molecules, for O2. If I fill the octets on these 2 oxygens that are bonded to each other, here's what I find. I count up and I have 2, 4, 6, 8, 10, 12, 14 electrons. But 2 oxygen atoms, because they have 6 dots apiece, don't give me that many electrons. 2 of these are only going to give me 12 electrons. So my count is too high. Here's what you do. To create multiple bonds, your first step is eliminate an electron pair from each of 2 atoms that are bonded to each other. So back to that last example, I have these 2 O's. Each of the O's has 6 electrons in lone pairs and makes a bond, and that's too many. So I'm going to eliminate an electron pair from each of those 2 atoms. So that'll go away, and that'll go away. I just take those pairs out. Now the next thing I'm going to do is I'm going to make an additional bond between those 2 atoms. So here's the structure that I've got so far. I've taken away 4 electrons by erasing those 2 lone pairs. I put 2 back in the form of a bond. What I've done is I've reduced my count by 2. Remember I had 14, I was supposed to have 12? Well, now it's right. And that's how you know what kind of a structure you have. You have a structure with a double bond in it. Let's work this out by doing a few examples. I'm going to do this example. I'm going to draw a Lewis structure for CH4. Well, CH4 has got carbon in it. Carbon's a group 4. Group 4s have 4 dots, 4 valence electrons. And then I've got hydrogen in there, which is column 1. That's 1 dot. But I have 4 of them. So I have 4 times 1 plus this 4. That gives me a total of 8 electrons in my structure. I want to keep that in mind because later on I have to match that count. Next thing I want to do is make a skeleton. Well, here's what I know. Group 4s, like carbon, tend to make 4 bonds. And I have 4 hydrogens to attach. Hydrogens have to be on the outside. So what makes sense is I'll put my 4 hydrogens attached to that single carbon in the center. That's a reasonable skeleton. The next step is I have to make sure I have full octets. Well, I do. Hydrogen only needs a full duet. Remember, hydrogen doesn't support 8 electrons. But my carbon does. And if I imagine a box around carbon, all 4 sides of the box has a pair of electrons. Remember, a bond is 2 electrons. So this carbon is stable. That's a full octet. Now, the last thing I have to do is make sure that I have 8 electrons in my structure to match this count. 2, 4, 6, 8. Okay, I've got it. So that's probably a good structure for CH4. CH4 is methane. That's what's in natural gas. Let's try another example. This example is C2H4. This is called ethene. Ethene is found in fruits and vegetables when they ripen. Well, let's make our dot notation. Again, we have carbon and hydrogen in there. Carbon has 4 dots, and there's 2 of them. And then we have 4 hydrogens again with 1 dot because they're in column 1. So these 4 make 4 electrons. 2 column 4s, all told, make 8 electrons. So when I add it together, I'm going to have 12 electrons that are going to go in my structure. Well, now let's make a skeleton. Because I know my hydrogens are going to go on the outside, and because I know carbon wants to make 4 bonds if it can, I'm going to put my 2 carbons in the middle, and I'm going to put my hydrogens on the outside. And I'll make it symmetrical by putting 2 carbons on each side. Okay, there's a skeleton that works pretty well. Now, the next thing I want to do is make sure I have full octets, and I don't. These carbons, if you imagine that box around there, have 3 sides covered, but the 4th side isn't. So I need to put another pair in there. That's a full octet. That carbon is now stable. And I'll do the same thing for this other carbon. Now, here's what I find when I do my count. 2, 4, 6, 8, 10, 12, 14 electrons. But that's not how many I'm supposed to have. I'm only supposed to have 12. So remember, in cases where your structure has too many electrons, you want to, first of all, eliminate an electron pair from each of 2 atoms that are bonded to each other. Well, that would be the 2 carbons here. So I'm going to take my eraser, scrub those off, and then the second thing you want to do is draw another bond in between those 2 atoms. So now I have a double bond between these 2 carbons, and when I make my count, it's 2, 4, 6, 8, 10, 12, and that's the correct count. So my structure, I'll just clean it up a little bit, should look like this. Double bond between the 2 carbons. Let's do another example. This is C2H2. This is ethine, or the common name is acetylene. If you've ever used a welding torch, oxyacetylene torch, you've used this gas. Okay, let's again make our electron count. We have 2 carbons in there. Carbons are group 4, so 2 of those are going to give me 8 electrons, and now I have 2 hydrogens. Hydrogens are column 1, so the 2 of those are going to give me 2 electrons, and all added together this gives me 10 electrons in my structure. Make a skeleton, and just like last time, I want to put the carbons in the middle, hydrogens on the outside, like that. And the carbons can't make 4 bonds here the way the skeleton's laid out, because we just don't have enough hydrogens to attach to them, but you make as many bonds to the carbon as you can. Now I check for full octets. Imagine my square around the carbon. Neither one of these carbons has a full octet. They each have 2 bonds. That's 2 electrons and then 2 more, but I need 4 more to make a full octet. So the other 2 sides get lone pairs. Now I count. 2, 4, 6, 8, 10, 12, 14 electrons. I'm only supposed to have 10. So I'm going to have to reduce my count considerably. Well, the first thing I'm going to do is erase a pair from each of 2 bonded atoms. So scrub off that pair, erase that pair, and I'll replace that missing pair of pairs with another bond. And then I recount. 2, 4, 6, 8, 10, 12. Still too many because I'm supposed to have 10. So I do it again. And then I put a third bond in between the 2 carbons. So you can do more than a double bond here. You just keep going until it works out. Okay, now I'll make my count. 2, 4, 6, 8, 10. Well, that's the correct count, and so that's the structure of acetylene.